ammonia is NH3, and amine, we simply replace one or more of these hydrogens with an alkyl. Okay? It says ammonia is a weak base. Amines are therefore organic bases, and they're all weak bases. So they have a Kb ionization constant. Amines can be classified as primary, secondary, or tertiary. Okay, so first off, a primary amine, only one hydrogen of ammonia is replaced. So an example would be this compound methylamine. Normally ammonia is NH3, here it's NH2 because we replaced one of the three hydrogens. Secondary amine, two hydrogens are replaced. We have two alkyl groups attached to nitrogen. We'll make this dimethylamine. There's only one hydrogen still on the nitrogen. Tertiary amine, all three hydrogens are replaced. So there are no hydrogens left, we just have three carbons, three alkyl groups attached. Now the thing to note here is when we classify these as primary, secondary, or tertiary, we are looking at the nitrogen. For alcohols, I just say it's different from alcohols. An alcohol, they all have an OH, right? And so we could have something like that. That would be a primary alcohol. Okay. This would be a secondary alcohol. Okay. And you notice the nitrogen here, right, has two nitrogen-carbon bonds. Here the oxygen, right, oxygen is got to have an OH, so oxygen just forms two bonds, so there's just one bond to the carbon. So what we're looking at for the oxygens is the carbon here. Right? So we focus on this, what we call the alcoholic carbon. Okay? A tertiary alcohol we're focusing on that alcoholic carbon. So with amines we're looking at the nitrogen, with alcohols we're looking at this carbon. So if we look at this compound here, let's say we have is this a primary, secondary, or tertiary amine? Okay. Well, yeah, granted this carbon is a secondary carbon because it has two carbon-carbon bonds. We are still looking at the nitrogen, and there is only one carbon-nitrogen bond. Highlight that one here, right? So this is primary, not secondary. The reason why we classify these as primary, secondary, tertiary, because it has implications for their physical properties. Implications for the physical properties. This is also different from alcohols. If you recall, when we classified alcohols as primary, secondary, tertiary, it has implications for its chemical properties, notably its oxidation. A primary alcohol could be oxidized to an aldehyde and then to an acid. A secondary alcohol could be oxidized to a ketone. Tertiary alcohols could not be oxidized. Well, when we talk about primary, secondary, tertiary with amines, we don't even talk about oxidation reactions for amines, but we will be talking about the difference between primary, secondary, and tertiary with regard to the physical properties. Okay, so naming these guys. There's a couple different ways to name them. There's an IUPAC names. I'm going to omit the formal IUPAC names, and we will just focus on simple amines and amides and pretty much look at just the common names. When you name an amine, it's similar to, it's similar to naming ethers. With ethers, we just named the two alkyl groups that were attached to the oxygen and then said ether. Same thing here. We're going to name the two alkyl groups and then amine. So the first guy up here, right, we have a methyl group. So this is methylamine. Okay. This is likewise a primary amine. We only have one alkyl group. It happens to be an isopropyl group, so we could have, I'll just write it up here, the name. This is isopropyl amine. Notice this is isopropyl alcohol, but this is a secondary alcohol. Isopropanol. Okay. Now for this secondary amine up here, we have two methyl groups, so this would be dimethylamine. And here we have three methyl groups, so trimethylamine. What if you had two different types of alkyl groups? So we say we had a methyl group attached and an ethyl group. Right, we simply alphabetize them. E comes before M, so this is ethyl, methyl. E comes before M, ethyl, methyl, amine. Another amine you should be familiar with is the one aromatic amine we talked about way back in chapter 10 with, actually, sorry, chapter 11. This is aniline. Okay, so here we go with the physical properties of amines. The hydrogen bonding amines depends on their classification. As primary, secondary, or tertiary. It's these hydrogen bondings and really the interparticle interactions that govern physical properties. Primary amines have boiling points and solubility similar to alcohols. Actually, it's going to be a little bit lower than alcohols. Should say slightly lower than alcohols, of obviously the same size, same molecular weight. Secondary amines have boiling points that are lower than primary amines, and tertiary amines have boiling points that are, I'll just say, the lowest. So again, primary amines, let's use aniline. It's a big, benzene ring here, but it's still a primary amine. Right. And it has two hydrogens. The nitrogen is more electronegative than the hydrogen, so it's going to have a partial negative. The hydrogens are partially positive. Okay. And so I can draw another aniline molecule here, and we have hydrogen bonding between two aniline molecules like that. Or I can put another one down here. Again, the hydrogen is partially positive, the nitrogen would be partially negative, and so we could form a number of different types of, actually there's one more here, I could put a hydrogen bond between this nitrogen and the hydrogen of another. So primary amine has a nitrogen and 2 hydrogens, so you can form 3 hydrogen bonds. So say can form 3 hydrogen bonds. Why is that? We have 1 nitrogen and 2 hydrogens. With the secondary amine, we still have 1 nitrogen, but only 1 hydrogen. So we'll draw, keep it simple here, we'll draw dimethylamine. And we'll put another guy down here. So we have this hydrogen bond again between the partial negative on the nitrogen, partial positive on the hydrogen, but because we have 1 fewer hydrogens, that's why secondary amines have lower boiling points than primary amines. With tertiary amines, there's only 1 nitrogen, no hydrogens, so no hydrogen bonds. If there's no hydrogens, how can you have a hydrogen bond, right? There's no hydrogens on this trimethylamine, so you can't have hydrogen bonds, so they have the lowest boiling point. Like ammonia, lower molecular weight amines have strong, unpleasant odors. And you might be thinking, well, ammonia, yeah, it has a pronounced, very characteristic odor, but is it really strong and unpleasant? You're probably not used to actually inhaling pure ammonia. What you experience as ammonia may be in a cleaning fluid, which is quite dilute. If you use concentrated ammonia and you take a whiff of that, your eyes will water, you'll gag, you'll choke. You really wish you had not done that. It's not pleasant at all. Elaborating here a little bit on the odors, one of the things that I forgot to mention in lecture, as I just realized here, there are a couple different amines. You could have a compound that actually has 2 amino groups on it. Okay, this would be 1,4-diamino, 1,4-diaminobutane. Right. This would be the IUPAC way of naming it, because the amines are treated as substituents. So 2 amine groups, so it's diamino. Here on carbons 1 and 4. And to give you an idea of the unpleasant nature of the odor for these guys, this guy is also called putrescine. It's the smell of rotting fish. There's another one with just 1 carbon more. It's 5 carbons. It'd be 1,5-diamino pentane. And it goes by the kind of the nickname of cadaverine. And it smells like the odor of rotting flesh. Alright, so yeah, amines are unpleasant odors. Right. Ionization of amines, the reaction with water, right? So this is just like ammonia. Ammonia plus water, what happens? Hydrogen ion is donated from water to the amine. We get the ammonium ion. NH3 becomes NH4+, and what's left of the water is the hydroxide ion. Something very similar happens with amines, and if you notice, the bonding that occurs here, the reaction that occurs here, is to the nitrogen. not to the hydrogen. So it doesn't matter if it's primary, secondary, or tertiary. All that matters is that there's a nitrogen. And you know, in a primary amine, we have 2 instead of 3, but really the same sort of thing happens. So let's take a look at a primary amine. Add water to this. Right, water is donated to the nitrogen. And when nitrogen forms 4 bonds now, it's got 4 bonds, there's going to be a plus charge on that nitrogen. What's left of water is a hydroxide ion. These are weak bases, so it's actually an equilibrium. There's a Kb that governs this equilibrium constant. The name of this amine is methylamine. Right, we've seen that before. This is the methyl what? The methyl ammonium ion. Okay. Salt formation. An acid plus a base gives you a salt and water. This time the base is actually the amine. So base and acid gives you salt and water. We're actually not going to form water in this case, so I cross that off. We'll just use, there's a couple different ways of looking at it, but the way I'm going to draw it, no water is formed. We're just going to get the salt. So let's use aniline. We'll react this with HCl. These guys combine, and so what was NH2 is now NH3, and of course this nitrogen now with 3 hydrogens and a bond back to the ring, it's got 4 bonds, and so it has a plus charge. The chloride ion is a counter ion, right? So this is, if you remember, methylamine becomes methylammonium. We got this IUM ending. Aniline becomes this aniline. We have this IUM ending, anilinium chloride. The main thing here is an amine plus an acid will give you a salt, this anilinium chloride. Right. Amide formation, or amide, I don't care which way you say it. Here we have we're going to add an acid. Functionally it's an acid, but what we're going to show is an acid chloride or an acid hydride to an amine to form an amide. Right, so we have the amine, and keep things simple in this case, we'll use methylamine. And for starters, I'm just going to use acid and acid chloride. And I'm going to draw the chloride in a slightly different fashion, so kind of backwards maybe. Okay. So what happens here now is the nitrogen, it's got an unshared pair of electrons, it bonds to this carbonyl oxygen. This bond breaks, and so the chloride ion is left by itself, and what we end up getting, right, the nitrogen now is going to be bonded to this carbonyl carbon. And now remember, nitrogen usually forms just 3 bonds unless it's an ion. We're not forming an ion, we're forming an amide. So there were 2 hydrogens here, but now there's room for only 1. What happened to that other hydrogen? Well, it came off and combined with the chlorine here to form hydrochloric acid. So that's one way, right? This here is an amide linkage. An amide is essentially it's a derivative of an acid, really, right? So normally you think of, okay, here's an acid, and there's going to be, you know, if this was I'll make another carbon here. If this was acetic acid, I have an OH, but instead have the nitrogen. So what we're looking at for an amide linkage, and actually got 2 more bonds coming up here. For an amide linkage, we're looking for the carbonyl of the acid bonded to the nitrogen of an amine, or it could just actually be ammonia. So actually let me use, instead of methylamine, let's just use ammonia. For this next one. Ammonia will react this with an acid anhydride. I drew this structure in class, and essentially it's 2 acids linked head to head, and anhydride, an acid anhydride means, anhydrous means you remove a molecule of water. So here we stuck 2 acetic acid molecules together and removed a molecule of water. So it looks something like this. And again, the nitrogen, unshared pair here, and the nitrogen goes, bonds to that carbonyl carbon. Okay. This bond here breaks, so let me just, that bond will break, and we're left with the acetate ion, CO minus. And because we just used ammonia, there are no alkyl groups attached to that nitrogen. Okay. Now as far as naming amides, I skipped over that. I will talk just a little bit about it here, but when you name amides, you essentially start off with the acid, because there really are derivatives of acid. So this was acetic acid. Okay. So acetic acid becomes acetamide, or this would be an IUPAC nomenclature, ethanamide. Acet for acetic acid, and then simply amide. Right? Or for IUPAC about it, ethanamide. Ethanoic acid becomes ethanamide. Now this compound up here, again, it started with acetic acid, but actually the acid chloride here, but it's still 2 carbon. Right? So 2 carbon acid is acetic acid, so it's going to be acetamide, but we have a methyl group attached to the nitrogen. So when we name this, it's going to be N-methyl acetamide, or N-methyl ethanamide. The N here, right, this means we have a methyl group attached to the nitrogen. So down here they talk about naming amides. I did a little bit there. I'll give you some more examples in a moment. Amide hydrolysis, this is done in actually 2 ways, either an acid or base. Acid hydrolysis is the easier way, I think. Actually, I take that back. They both have some details you should know about. So let's just draw an amide here. Okay, so that's 3 carbons. That would be propanamide. And if I hydrolyze this with acid, so by the way, amides are also much sturdier than esters, so you can hydrolyze these, but it takes usually a little bit harsher conditions, higher concentrations, higher temperatures, longer period of time. And what we're going to do is we're just going to break that bond. Okay, so we add water back to this. So I'm going to use red. It's a hydrolysis, so hydro for water, right? So here, we make it on the reactionary HO. I'm going to put an OH, right? So there's the OH of water. We get the acid plus, where'd that other hydrogen go? Well, it bonds to nitrogen, so we get ammonia, right? Well, not quite. Plus NH3? Not quite, because what happens is this is still in the presence of, let's say we used HCl. This is going to then form NH4Cl minus, the salt, right? Because, yeah, we release a molecule of ammonia, but it's in the presence of this acid still, so it reacts to form the amine salt. It's actually just ammonium chloride, ammonium salt. But if it was methylamine, it would be methyl ammonium chloride. So that's what happens under acidic conditions. So acidic. Okay, get this out of the way. Under basic conditions, what happens? Let's make it a slightly different compound. Okay, so this would be N-methyl, right? We have a methyl group attached to the nitrogen, so N-methyl, and then 1, 2, 3, this was propanoic acid, so propanamide. This would be N-methyl. N stands for nitrogen here. N-methyl, 3 carbons is propane, so propan, and then just drop the E and add amide. Propanamide. Okay, we're going to hydrolyze this guy. We're just going to break this bond between the carbon and the nitrogen, releasing the acid and the amine. So in this case, the acid is this 3-carbon acid again, CH3, CH2. I'm going to draw it in a slightly different way. Draw it like that, COOH. Plus the amine. Okay. So again, we're adding, essentially it's like adding water across that bond here. The OH ends up on the, actually let me redraw this. Oops. Let me redraw it this way so it will be easier to see. The OH ends up on the acid, the hydrogen ends up on the amine, so you get methylamine and propanoic acid. Except, remember, this is under basic conditions. So let's say we use potassium hydroxide, right, under basic conditions. So what really, a better way to think about this is, again, this guy is still in the presence of this potassium hydroxide. And what happens when we have an acid and a base like potassium hydroxide? We will get the carboxylate salt. So again, this is going back to the last chapter. Here's our carboxylate. Right? So we get the carboxylate salt. All right, so then, under acidic conditions, we break this amide, we get the carboxylic acid and the amine salt. The amine salt. Under basic conditions, we'll get the amine, right, and the carboxylate salt. So there's some parallels between both acidic and basic, and also there's parallels between this sort of reaction and acid and base hydrolysis or saponification of esters, right? We call the base saponification, base hydrolysis of esters saponification. So we can hydrolyze an ester either under acidic or basic conditions. We get slightly different products depending upon the reaction conditions. Same sort of thing here. So common medical uses for amines and amides. With amines, these are pain relievers or analgesics. I before E, except after relievers, pain relievers. So there was codeine and morphine. Those are also, by the way, those are alkaloids, as I speak of alkaloids down here. They're also stimulants. These are amines. So we had caffeine, amphetamine, nicotine. Those are all stimulants. Right? Amides, if you remember, I won't get into the names of all these, but amides, these guys tended to be, well, they're also pain relievers, analgesics, pain relievers as well. But instead of being stimulants, they tend to be depressants. Right? Depressants. So the phenobarbital, for example, and Valium. So common use, medical uses, right? Depressants. Understand the medical significance of amine salts. So an amine such as aniline, and if it's more than 5 carbons, it's not going to be soluble. Actually, they talked about this with regard to, I think, cocaine. Would be another amine that's a stimulant and a pain reliever. But we'll just use aniline here. An amine salt, if we add HCl to this, right, we get the anilinium chloride again. Right, so there's your amine salt. This guy is insoluble. It's more than 5 carbons, so insoluble in water. But the amine salts are soluble. Also, these guys are all solids at room temperature, whereas lower molecular weight amines, such as this, would be a liquid. So it's a little bit easier for storage and whatnot and shelf life if it's a solid. That's another reason. But because these are soluble, they're going to, in water, they're soluble in tissues, they're absorbed better. So that's why many drugs that contain amines are formulated as amine salts. Differentiate amines and amides in physical and chemical properties. Okay, amines, say the primary and secondary, these guys have hydrogen bonds, so they're more polar, higher boiling points, and solubility. Depending upon, and actually they also classified amines as primary, secondary, tertiary. This would be amides. This would be a primary amide because it has only 1 nitrogen carbon bond. This is an amine structure amide. Because an amide, I did it again. Amide here. We'll draw the structure of benzamide. So this is benzoic acid. We reacted. Okay, so benzamide. So notice this has only 2 hydrogens, right? This has 2 hydrogens. So this can still hydrogen bond, right? It's still soluble. Okay. But whereas amines had kind of nasty unpleasant odors, these would be so bad. Right? Amides, they're not as smelly. But you can also get this here would be a primary. Here, this is a primary amide because there's only 1 nitrogen carbon bond. This would be secondary because we have 2 nitrogen carbon bonds and only 1 hydrogen, so it's not quite as polar because you can only form 1 hydrogen bond here, whereas with the benzamide you can form 2. Right? So generally speaking, these guys are not as polar, and we say odor is less as well. Odor is less than that of amines. An alkaloid, what is an alkaloid? This is an amine with pharmacological properties. I think the book used the term physiological, but pharmacological properties, and it's derived from plants. The other thing about these alkaloids, they end in the suffix -ine. So up here, right, codeine, morphine, caffeine, nicotine, cocaine, they all end in -ine, and they're also slightly basic because they have that amine. And the one alkaloid I'll tell you about is quinine. Quinine also ends in -ine. There's a neat story about quinine and malaria, but the anti-malarial properties, so this is an anti-malarial, it's an anti-malarial drug, is owes anti-malarial properties to its slightly basic conditions. The bacteria that causes malaria cannot replicate when quinine raises the pH of red blood cells. So anyway, because it's slightly basic. So quinine also, you find quinine in what? Tonic water. And if you have any tonic water at home, it is not seltzer water. Often it is carbonated, but it doesn't have to be. But if you take a sip of tonic water expecting it to be seltzer, you'll know right away it's slightly basic because it has a very bitter taste. Remember, bases taste bitter. Okay.